It's Dr. Juliet again. Welcome to Jules Summit Biochemistry. Still on the subject of enzyme kinetics, today we shall be looking at how to derive Lineweaver-Burk equation from Michaelis-Menten equation. From our last class, we saw the derivation of Michaelis-Menten equation based on the steady-state assumption, where the concentration of the enzyme substrate complex is in equilibrium with the concentration of the enzymes. Now, let's tackle this question. Transform Michaelis-Menten equation to Lineweaver-Burk's equation and sketch the plot, which is Lineweaver-Burk's plot. From our last class, we saw the derivation of this equation, the Michaelis-Menten equation, VO, which is initial velocity, is equal to maximum velocity times constant substrate concentration divided by Km plus substrate concentration. Remember, Km is the substrate concentration at half maximum velocity. Now, the first step is to cross multiply. So we have VO multiplying everything here equal to Vmax S. And then we divide both sides by initial velocity. So all of this divided by VO, all of this divided by VO at this point. So we can call this equation 1, we can call this equation 2. So if you divide this VO strikes at this, so we're left with Km plus substrate concentration. And then this remains the same, nothing is lost over here to give us equation 3. And then the next step, which is the final step, is to divide both sides by Vmax times substrate concentration, which we have over there. Now remember, this is Km, so we divide Km by Vmax substrate concentration, we divide substrate by Vmax substrate concentration, we divide the whole of this at the right hand side also by Vmax substrate concentration, which is what we have here. So we have all of this remains the same, nothing is cancelled. Then over here, S divide S to give us 1, which is 1 over Vmax remaining there, and then Vmax X divide everything here remaining 1. So we now have 1 over VO. So what remains here is 1, and the numerator, what remains here is 1. Denominator here is Vmax, denominator here is initial velocity. And so since we know this is the subject of the formula, we'll write it this way. 1 over initial velocity is equal to Km divided by Vmax substrate concentration, the same as this. Here we now do 1 over. So if you multiply this and this, you return back to this. Why do we separate it this way? To aid you in the plotting of your graph. To aid you in deriving the plot. So you know what to plot on the y-axis and what to plot on the x-axis. So this and this is exactly the same. We're separating 1 over substrate concentration from the whole of this, so it can help aid in this plot. And then plus 1 over maximum velocity. And now this is the Lineweaver-Burk equation you're requested to derive from Michaelis-Menten equation. So with this, you can now get your plot. The y-axis, you plot 1 over initial velocity. Your x-axis, you plot 1 over s. If that is the case, according to mathematics, to get a graph, it means that whatever is attached to your x-axis value will be the slope. So the slope of this graph is Km over V max. And we know whatever is left there after the plus should be your intercept on the y-axis. So this is the intercept on the y-axis, 1 over V max. This will call what we call the Lineweaver-Burk plot. So we can see how in 4 or 5 steps, we have just 4 steps. We have our Lineweaver-Burk plot from our equation from our Michaelis-Menten equation. Very simple. You cross multiply first step, you divide both sides by initial velocity second step, you divide, and lastly you divide both sides by Vmax times substrate concentration. I hope we'll be able to simplify this for you. We ask that you keep following us, like what we do, share our tutorials, videos and text, and do well to follow us on other channels. We are on WhatsApp and we're also on YouTube for more video tutorials on biochemistry. Until I see you again, thank you, and it's bye-bye for now.